Hello learners, today we will discuss some more details about the induction motor. In the last session, we have discussed about the principle of operation, the construction and some phenomena like cogging and crawling. Now, we discuss some detailed operations of induction motor. The first one comes the equivalent circuit. Now, this concept is same as that of the transformer. In our last session, we have told you that there is a similarity between the induction motor and transformer. So, there is also similarity between their equivalent circuit. Just as we have equivalent circuit for transformer, the same can be utilized for the induction motor, but with a slight difference. The induction motor is similar to transformer with the exception that its secondary windings are free to rotate. As we notice in the transformer, it is easier if we can combine these two circuits, that is the primary circuit and the secondary circuit in one circuit, but there are some difficulties, and that difficulty is that the secondary in induction motor is rotating in nature. So, however, the equivalent circuit as suggested from the transformer is shown in the screen. We have a R1, we have a reactance X1, where R1 is the stator winding resistance, X1 is the reactance of the stator winding, RC and XM represent the no load parameters. Now, mind it, the no load current in the induction motor is 30% of the full load current, while in case of transformer it was only 2 to 3% of the full load current. Now, these are the two coupling windings, and JXR is the rotor reactance and RR is the rotor reactance, but this rotor reactance and the rotor resistance are not constant, that we will see later on. So, when the rotor is locked, that is when slip is equal to 1, the largest voltage and rotor frequencies are induced in the rotor. On the other side, if the rotor rotates at synchronous speed, that is when slip is equal to 0, the induced voltage and the frequency in the rotor will be equal to 0, that we have already discussed. So, what conclusion we are finding, that the induced EMF in the rotor circuit is function of slip, and therefore, we can write this induced EMF ER in the rotor is equal to slip times the induced EMF when the slip is equal to 1. So, ER is equal to SER naught. This ER naught is the largest value of the rotor induced voltage obtained at S is equal to 1, that is when the rotor was locked. The same is true for the frequency. We have already derived that the rotor frequency is equal to S times the supply frequency. So, what is its net effect? The net effect is on the rotor inductance. How? We already know from the basic principle of the circuit theory that the rotor reactance is given by omega L, where omega is 2 pi f. 2 pi f means 2 multiplied by the pi constant multiplied by the frequency multiplied by the inductance will give you the total reactance. So, the frequency of the induced voltage in the rotor changes, and hence the reactance of the rotor circuit will also change, and therefore, we will get the rotor reactance XR as S multiplied by XR naught, where XR naught is the rotor reactance at the supply frequency, that is when the rotor is blocked. So, what conclusion we are getting, that both induced voltage and the induced frequency are variable quantities, that they vary with the slip, and therefore, we can redraw the rotor equivalent circuit as shown on the screen. We have a variable voltage source ER is equal to S times ER naught, which is connected in series with the rotor reactance, which is also variable, and its value is given by S times XR naught, and we have a fixed rotor resistance RR. So, we can calculate now the rotor current. The rotor current will be given by the simple circuit theory principle. Rotor current IR is equal to ER upon the rotor impedance, which is nothing but the phasor sum of rotor resistance and the rotor reactance. You can see from the screen, which can be further simplified by writing ER as SER naught and the rotor impedance as RR plus JXR naught. Again we simplify it dividing both the numerator and denominator by S. So, we get the following formula for the rotor current, that IR is nothing but ER naught upon RR upon S plus JXR naught, where ER is the induced voltage and XR is the rotor reactance at block rotor condition, that is when slip is equal to 1. So, now with this formula our rotor equivalent circuit will look like this. We have a fixed voltage ER naught, we have a fixed reactance JXR naught, and we have a variable rotor resistance whose value is given by RR upon S. So, now we can combine the primary circuit and the secondary circuit, and ultimately we obtain the equivalent circuit of the induction motor as shown in the screen. Also, what we have done, that we have referred the secondary quantities with respect to the primary. So, we have a R1 stator resistance, X1 stator reactance, we have a no load branch consisting of two parallel branches RC and XM, and on the secondary side we have a rotor resistance as R2 upon S and rotor reactance X2, where X2 is equal to effective turn ratio multiplied by XR naught and rotor resistance R2 is equal to square of the effective turn ratio multiplied by the fixed rotor resistance. This effective turn ratio is defined as the ratio of stator turns upon the rotor turns. Now, after drawing the equivalent circuit, we come to the what are the different power losses in the induction machine. Now, three types of losses are there. First is the copper losses. Definitely the copper loss is due to the windings. Two types of windings are there, the stator winding and the rotor winding, and therefore, there will be losses due to the stator copper loss and there will be rotor copper loss. The stator copper loss is given as I1 square R1 and the rotor copper loss is given as I2 square R2. Now, core is also being utilized in the stator, therefore, there is also a core loss which will be denoted by P core. Now, as the name suggests, it is an rotating machine, therefore, there will be some mechanical loss due to friction and windage. And how this power flow in the motor after considering the losses, let us look to the screen. How power flow in induction motor? We supply a 3-phase supply to the stator winding. So, this is the input power and it is given by √3 times the terminal voltage, load current and cos of theta, where theta is the phase difference between the terminal voltage and the line current. Now, this power goes to the stator winding. In the stator winding, there is a stator copper loss that will be subtracted from it. Then there is a stator core loss will be there, that will be also subtracted from it. After subtracting these two losses, we get an ultimate power in the air gap, and this power is known as power air gap, PAG. It is represented by PAG as you can see from the diagram. Now, this power goes to the rotor. In the rotor, induced EMF and induced current will flow, and due to the flow of the current, there will be rotor copper loss, which is represented by PRCL on the screen. This will get subtracted from PAG and we will get an P conventional power. This is the gross mechanical power, and from this gross mechanical power there will be subtraction of the friction and windage loss and some stray losses, and ultimately we will get an output mechanical power which will be equal to load torque multiplied by the load speed, that is speed of the rotor. After going through the power flow diagram, let us look to some of the mathematical expression for the different powers. P input can be written as √3 times the terminal voltage, terminal current multiplied by the cos of theta, which can also be written in terms of phase quantity as 3 times the phase voltage, phase current cos of theta. The copper losses can be written as 3 times I1 square R1 because 3 windings are being used, and the air gap power is nothing but P input minus the sum of the 2 losses, that is copper loss and the core loss. Rotor copper loss can be written as 3 times I2 square into R2, and therefore, we will get a net mechanical power as P air gap minus the rotor copper loss. The output power is equal to the net mechanical power minus friction windage loss and the stray losses. Now, we are modifying our equivalent circuit, and that also on the secondary side. On the primary side, the parameter remain as it is, that is, we have a supply voltage V phi, R1 X1 are the resistance, the reactance of the stator windings, RC and XM represent the 2 parallel branches representing the no load parameters. However, on the secondary side, we divide this rotor resistance, which was previously represented by R2 by S. Now, we will break into 2 parts. One will be the fixed resistance R2 and another will consist of R2 1 minus S upon S. This R2 1 minus S upon S is the equivalent to the mechanical load, and X2 will remain as it is. So, again the power relation will somewhat change, and therefore, we will get the mechanical power which was previously air gap power minus the rotor copper loss. Now, we can define as a P RCL 1 minus S upon S. Similarly, the output power is same P conventional minus P friction and windage loss minus P stray loss. Now, next come the torque and the power relationship we will derive with the help of the Thevenin theorem. Now, this is the equivalent circuit. Now, we apply the Thevenin theorem across the point A and B, and we will convert into Thevenin equivalent circuit. The Thevenin equivalent circuit will look like this. We have a Thevenin voltage, we have a Thevenin resistance as well as reactance, and on the load side we have an reactance X2 and the rotor resistance R2 by S. So, by mathematical calculation, you can see from the screen we have derived the Thevenin voltage conventionally as we derive by using the Thevenin theorem. Similarly, we have calculated the Thevenin resistance as well as the Thevenin reactance. After simplifying that Thevenin model, we obtained the following torque equation as you can see from the screen. We find that this torque is proportional to the rotor resistance R2, and if we plot the torque speed characteristics, the following torque speed characteristics is obtained. You can see that it has some starting torque, it reaches to a maximum torque, and then again this torque will goes on decreasing with the speed. So, what are the different comments related to this torque speed? The induced torque is 0 at synchronous speed, very clear from the diagram. The second, the curve is nearly linear between no load to full load. In this range, the rotor resistance is much greater than the reactance. So, the rotor current torque increases linearly with the slip. The third conclusion we can draw from this torque speed characteristics, that there is a maximum possible torque that can be exceeded. This torque is called pull out torque and is 2 to 3 times the full load rated torque. Further, the starting torque of the motor is slightly higher than its full load torque. So, the motor will start carrying any load it can supply at the full load. One more conclusion we are getting, that the torque of the motor for a given slip varies as the square of the applied voltage. Another important point, that if the rotor is driven faster than synchronous speed, it will run as a generator, converting mechanical power to electrical power. But in the beginning, I have told you that these rotor induction generators are being seldom used, therefore, this is not of so much of use. This is the complete torque speed characteristics for both motoring action as well as generating action. You can see from the screen. Another conclusion was that the maximum torque occurs when the power transferred to R2 by S is maximum. This condition occurs when R2 by S equal to the magnitude of the impedance RTH plus J times XTH plus X2. So, the slip at the maximum torque condition is obtained as follows, as you can see from the screen. This corresponding maximum torque of an induction motor is equal to the formula given on the screen. Further, we also find that the slip at maximum torque is directly proportional to the rotor resistance R2, and the maximum torque is however independent upon the rotor resistance R2. This rotor resistance can be increased by inserting external resistance in the rotor of the wound root induction motor, but this cannot be done with the squirrel cage induction motor. You can see from this diagram that as I am increasing or decreasing the rotor resistance, the maximum torque remains the same. Now, after going through the torque speed characteristics of induction motor, we will talk about the determination of motor parameters. Now, due to similarity between the induction motor and the transformer equivalent circuit, the same test which are being used for transformer can be used to determine the motor parameters. Now, what are the different tests? The first test is known as DC test. Now, this DC test is meant to determine the stator resistance R1. The second test is known as no load test. It is used to determine the rotational losses and magnetizing current. Now, this is similar to the no load test as we have done in the transformer. Third test is known as blocked rotor test or also known as locked rotor test. It is used to determine the rotor and the stator impedance similar to the short circuit test in transformers. Now, let us talk these tests. First test is known as DC test. The purpose of DC test is to determine the stator resistance R1. A variable DC source is connected between the two stator terminals. The DC source is adjusted to provide approximately rated stator current, and the resistance between the two stator lead is determined from the voltmeter and the ammeter reading as shown in the figure. This is the experimental setup which is being used to determine the stator resistance. So, RDC is given by VDC upon IDC. Now, if the stator is Y connected, because it is a 3-phase winding, therefore, two connection can be used, either delta connected or star connected. So, if it is a star connected, the per phase stator resistance is RDC upon 2, and if it is a delta connected, the per phase stator resistance is given by 3/2 RDC. Next test we will discuss is the no load test. Now, in the no load test, the motor is allowed to spin freely. The only load on the motor is the friction in the windage losses. So, the P mechanical is consumed by the mechanical losses. The slip is very small. The equivalent circuit will reduce in no load test as shown on the screen, and therefore, at no load condition, the input power measured by the meter is equal to the losses in the meter. Also, the rotor copper loss is negligible because the rotor current is small, because R2 1/S is very large. So, the input power equal to the stator copper loss plus the core losses plus the friction in the windage losses. So, one parameter we have found out, that is the losses in the motor with the help of the no load test. Another test is the blocked rotor test. It is also named as a locked rotor test because in this the rotor is not allowed to move. A voltage is applied to the motor and the resulting voltage, current and power are measured. The AC voltage applied to the stator is adjusted so that the current flow is approximately full load value. Mind it, in case of the no load test, rated voltage is applied, but in the block rotor test, rated current is allowed to flow. With the help of the block rotor test, we can find out the stator and the rotor parameters. With the help of the measured voltage, current and power, we can find out the equivalent circuit parameters R1, R2, X1 and X2. Thus, by combining these three tests, we can find out all the equivalent parameters of an induction motor. Dear learners, I am summarizing what I have told you today. In today's lecture, we have discussed about the equivalent circuit of a induction motor. We have also discussed about the power flow diagram of the induction motor, where I have told you that what are the different powers at the different position of the induction motor. We have also discussed about the different tests related to the induction motor to find out the equivalent parameters. Hope you have enjoyed this lecture. Thank you very much.